Hey everybody, welcome back. So in this video what we're going to do is talk about how do you actually find this wave function that describes this matter wave. Okay, so again, it's going to be very mathematical. I'm going to do a derivation of the so-called time-independent Schrodinger equation. You're welcome to watch the derivation. If you want to fast forward, I understand, but it might be worth 10 or 15 minutes to watch the derivation, just for the sake of knowledge. Okay, so let me scroll down. Whoops, I'm so sorry. Let me scroll down a little bit so we got some more room. Okay, so here we go. So I think I do ask, there are a couple quantum physics study questions about the Schrodinger equation. I think one of them is, where does it come from? And what I mean by that is, what physical concepts do you use? What physical laws? So I'll point that out. In fact, the first thing that you do, so what we're trying again we're trying to figure out how do you find this wave function for a particle that's moving in 1D. And again, we're only looking at the 1D case. Okay, so the first thing we borrow from classical physics, non-quantum mechanics, is the idea of the wave equation. Because every wave, whether it's a wave on a string, a sound wave, a water wave, is going to obey a second order differential equation, partial differential equation, and it's of this form. So for instance, if you look at a wave on a string and you call the displacement of a point, this represents a string. Maybe there's a little pulse traveling along the string. This is the x-axis. What you do is you label traditionally the vertical axis the y-axis. So you can describe the y value of a point on the string at some position x at some time t. This would be the wave function for the wave on the string. Well, in that case, the wave equation is going to look like this. The second derivative of y with respect to x is going to be 1 over the speed of the wave squared times the second derivative of y with respect to time. Now these are partial derivatives because y is a function of x and t. Okay, so any wave that's traveling in one dimension will obey a differential equation of this form, where the speed of the wave is that v. Okay, now you may call the wave function something else other than y. For instance, for the matter waves, we call the wave function psi. So we do expect that this capital psi, which is a function of x and t, should obey a similar wave equation. So that's going to be our starting point. So, whoops, this is capital psi, x of t. Okay, now the next thing that we do, and this harkens back to differential equations. You might remember this in differential equations. What we're going to do is make a special assumption, which is why this is going to be time independent. We're going to assume that the wave function is separable. And you might recall this again from differential equations. What we mean by that is it's a function of both x and t, but it can be written as the product of a function only of x times a function only of t. That's what we mean by separable. And traditionally, the function of x is indicated with a lowercase psi. It doesn't have the bars on it, and a phi. Okay, so psi of x, little psi of x times little phi of t is how we can write this wave function. Now, we also are going to assume a very special time dependence. So we are going to assume that phi of t is harmonic. So either a sine or a cosine, it doesn't matter. I'm going to take the cosine of some angular frequency times t. We're going to assume that. Okay, and you'll see what happens if we make this assumption. And again, this might seem restrictive, but it's not as restrictive as you first might think. Okay, so now, guys, we get to do some derivatives. You get to help me out. So the first derivative with respect to x, well, if we write capital psi as this product, that's just going to be the derivative of little psi with respect to x times phi of t, which we're assuming is a cosine of omega t. Okay, let's take the derivative again. So we take the derivative with respect to x again to get the second partial derivative. So that's just going to give me the second derivative of little psi with respect to x times the cosine of omega t. Okay, now let's do the time derivatives. We'll do them over here. Let's do the first derivative with respect to t. Well, if phi is a cosine of omega t, the cosine is going to turn into a minus sign, and I'm going to pull out an omega. So I'm going to get minus omega times the little psi of x, that function, times the sine of omega t. And then we're going to take the derivative, the partial derivative, again with respect to time. So the sine will turn into a cosine. I'll pull out another omega. So I'm going to get a minus omega squared times that little psi function, and that sine is turned back into a cosine. Okay, so now what we're going to do is we're going to stick these second derivatives here back into this assumed wave equation. Okay, so if we do that, we'll make sure you can see the wave equation. There it is. What we're going to get is we'll have d squared little psi dx squared times the cosine of omega t is equal to minus omega squared over v squared psi of x times the cosine of omega t. All right, now you can see what happens now. These cosine functions are going to divide out. So by assuming a harmonic time dependence to that separable function, the time dependence drops out. That's why what we're developing is called the time-independent Schrodinger equation. There is a more general time-dependent equation, but it's more general, and we're not going to worry about that in this class. Okay, we're going to stay with the time-independent, and we'll say more about it after we get this equation. Okay, all right, so now the next thing I'm going to do is I'm going to focus on that omega over v. Okay, so if you remember, for a wave, the speed of the wave is the wavelength times the frequency. Okay, now I'm going to write it like this. I'm going to write this as 2 pi f over 2 pi over lambda. And you're going to say, why did I do that? And I'm going to say, because I wanted to. That is equivalent to lambda times f. But then I recognize that 2 pi f is the angular frequency. And if you remember way back in part 1, 2 pi over lambda is what we call the angular wave number, little k, 2 pi over lambda. So if I make that substitution in for the v, my differential equation is going to look like this. I'm going to have the second derivative with respect to x of little psi is minus, can you imagine putting omega over k in for the v? You're just going to be left with minus k squared. And then I have the function little psi of x. Okay, I'm skipping a little bit of algebra, but I don't want to spend a whole bunch of time on the derivation. Okay, but so we use this idea, this wave idea of speed as wavelength times frequency. Okay, now what I'm going to do next is I'm going to bring momentum and energy into the discussion. Okay, so if you recall, for a matter wave, the momentum is h over the matter wavelength. That idea, again, is borrowed from the photon. The matter wavelength, or the Broglie wavelength, is h over the momentum. Okay, so I can write it like that. Now, what I can do, again, because I want to, I can write h over lambda as 2 pi over lambda times h over 2 pi. Okay, I recognize 2 pi over lambda as k, the angular wave number, and h over 2 pi, recall, I can abbreviate as h bar. Okay, so what I'm going to do is I'm going to replace that k right there with p over h bar, momentum over h bar, and that is going to allow me to write my differential equation as d squared psi dx, little psi dx squared equals, I'm going to have minus momentum p squared over h bar squared times psi of x. Okay, all right, so now what we do is, so we brought in the idea of momentum, right? Now we're going to use conservation of energy. Because what we're going to say is the total energy of this matter wave, this particle, is going to be conserved. So total energy, I'm going to use E for total energy, has two parts. It has motional energy, kinetic energy, big K, but there could be an interaction, and often there is, an electric interaction, electric force interaction, for instance, where you have a potential energy. So U is the potential energy of the particle or matter wave, okay? Now, kinetic energy, we know we can write as 1/2 mv squared. I'm not using relativistic mechanics. There is a relativistic version of the Schrodinger equation, but we won't worry about that in this class, okay? Plus potential energy. Now, if you look at 1/2 mv squared, if you remember that momentum is mass times speed, velocity, I can write 1/2 mv squared as momentum squared over 2m, and I want to do that. Okay, just put in mv for p, square it, and you'll get 1/2 mv squared. Okay, so let's solve this for p. Actually, p squared. P squared is going to be 2 times the mass times the difference, total energy minus potential energy. Okay? I want to put this in to the p squared up here. So then I have my differential equation is d squared psi dx squared is minus 2m over h bar squared times the total energy minus any potential energy times the wave function psi of x. Okay? All right. Then what I can do is I can multiply both sides by minus h bar squared over 2m and shift terms around. You can double check this, but here's the final version of my differential equation. It's going to look like this: minus h bar squared over 2 times the mass of the particle times the second derivative of the function little psi of x with respect to x plus the potential energy, which will be a function of position. That's potential energies are functions of position, times little psi of x equals the total energy, which is a constant, times the little psi of x. Okay, I'm going to put a big box around this. This is known as the one-dimensional time independent, because we assumed a harmonic time dependence for the spatial, the temporal part, time independent Schrodinger equation. And you see Schrodinger spelled a variety of ways. Sometimes without the little diacritical marks, it'll just be OE. Okay, but I'm going to write it like that in this notepad. That's the one-dimensional time-independent Schrodinger equation. Okay, so how does this work? Okay, so in practice, what you're going to have to do is you're going to have to be able to describe the potential energy function. So through interactions, this particle typically is going to have some potential energy interaction, some potential energy function. Describe that. Then what you try to do is you try to solve this equation for the psi of x. And this psi of x is commonly called the eigenfunction. And I'm going to use that term. If you've had linear algebra, if you've taken linear algebra, or maybe even in diffie-q, differential equations, you talk about eigenvalue problems. This is actually an eigenvalue problem. The reason we call it an eigenvalue problem is if you look on the left side involves what we would call operations on the eigenfunction psi of x. So the operation is you take the second derivative with respect to x, multiply by minus h bar squared over 2m, add to that the product of the potential energy times psi of x. So this whole left side is an operation on the function psi of x. What you will get out when you do that operation, you will end up with a constant times the original function. In fact, in quantum mechanics, you will see this equation written like this. Okay? This is sort of an advanced notation. What that h with the little caret means, this is known as the Hamiltonian operator. The Hamiltonian operator means you do this recipe. Again, you take the second derivative of psi with respect to x, multiplied by minus h bar squared over 2m. You multiply psi by the potential energy function, add those together, and you will get a constant times the original function. The E is known as the eigenvalue. Now, physically, what this means is that the eigenvalues are energies. So what happens in practice is you will get different solutions. There will be different eigenfunctions for different energy states. So each state, each eigenfunction will have a corresponding energy for that state. It's similar to what happens in the Bohr model, right? The solution that Bohr found for the hydrogen atom is that there are different states. Each has, right, its own energy. Well, formally, that's what happens here. So for a given system, there will be different quantized energy states with different E's, and those energy states will be described by an eigenfunction. All right, so that's what happens in practice. Okay, so where does this 1D time-independent Schrodinger equation come from? Well, it really comes from some classical physics ideas, namely the wave equation, right? Conservation of energy, and then we use also the idea of momentum of a matter wave, right? Okay, so that's where it's coming from. All right, now in the next video, what we will do is we will look at how to apply this, how to actually solve this equation for a very special potential energy function, okay? Look at the summary notes again, right? And this will summarize what you need to know. So really all you need to know is, can you write down the 1D time-independent Schrodinger equation, okay? And know what we mean by the eigenfunction, which are these little psi of x's, and the energies are the eigenvalues. The energies are quantized. So there are certain energies that go with certain eigenfunctions. Okay. Oh, one more word before we wrap it up. This whole time independent, right? This is still very valuable information. You won't be able, if you solve for these eigenfunctions and you find out what the energies are for these different states, that's really crucial information. You're not going to be able to say, when does the particle have this energy? So you won't be able to describe what's happening to the particle in time, but just knowing what are the allowed energies for this system and what do these eigenfunctions look like, that is very valuable information. For instance, if you're looking at an atom, You may not care when is the atom in this particular state. You just want to know what are the allowed energy levels of this atom. Okay, so time-independent Schrodinger equation, very, very, very valuable information can be gained from it. Okay, I'll see you in the next video where we look at an example. Bye-bye.